So here in lecture 5.3, we're going to complete our discussion of two-level logic synthesis. And in the previous parts of lecture 5, we talked about the idea of heuristically reshaping a cover of a two-level form to get a really high-quality, heuristically good solution. And we gave you a high-level tour. In this final part of the lecture, we're going to just take one of those steps. We're going to take the expand step. And we're going to do a little bit of a deep dive and open it up and show you how it works. And so there's some new ideas that are applicable in the computational Boolean algebra universe that we're going to see. And with that, we'll finish up on two-level logic synthesis, and then we'll move on next, in the next set of lectures, to multi-level logic synthesis.
So how does all this stuff actually work? Well, one of the things that's really very interesting is that the core representation for most of this stuff is positional cube notation cube lists. So this is just exactly like week one's lectures on URP tautology. Many of the heuristics use some clever ordering of the cubes and then operate on each cube in some sort of a ranked order. And they're mostly doing bit level PCN operations on the cube list. So it's actually all pretty understandable by you. And many of the rest of the operations are actually done as URP, unate recursive paradigm kinds of recursive descent, just exactly like week one's lectures. And in fact, the tautology algorithm that we showed you is a key part of Espresso. And with some work, you could actually read a lot of the primary source literatures here. So congratulations, we're actually making some real progress here. I want to look briefly at one step. Now let's pick one. Let's look at the expand step. And let's just take a step back and say, so what does it mean to expand a cube? Well, so here's a little product term. Here's a cube, and I'm listing it in positional cube notation. Just for clarity, x, y, z bar, w, that's this circle in this Carnot map right there. That's x, y, z bar, w. Right, so there's a little Carnot map here. It's 4 by 4 squares, x, y on the horizontal axis, z, w on the vertical axis. The top row is 1, 0, 1, 1. The second row, 0, 1, 1, 1. And then the entire 1, 1, x, y column is filled with 1. So that's what this cube, that's what this Carnot map looks like. If you were to expand a cube, what that means is that you remove variables from the cube. And so what that means is that, instead of x, y, z bar, w, you'd like a product term that had less literals in it. Because you know what you're looking for? You're looking for a smaller AND gate, right? So this thing is an AND gate with 4 inputs. Both of the examples that I'm showing in the middle of the slide are AND gates with 2 inputs. Removing variables from the cube removes inputs from the AND gates and makes you have less hardware. So what would happen if you removed YW? Well, if you removed YW, then you would be able to circle the top 2 by 2 set of 1s in the Carnot map, and you would actually get XZ bar. All right, that's what that one is. What would happen if you were to remove ZW? Well, then you would actually be able to circle the entire XY column of the Carnot map, and you would be able to get that cube. And so, both of those are perfectly nice solutions. I'll just say, both of those solutions are okay. The question is, how do you find something like that when you're dealing with thousands and thousands and thousands, maybe tens of thousands of cubes, and hundreds of variables? I mean, we need a computational algebra approach. We need something that's an operation and an algorithm. So it turns out that we can take the expand operation and we can transform it into a classical kind of computer science problem for which there are perfectly okay heuristics. So we're going to turn this into something called a covering problem. And you may or may not have seen a covering problem. So let me show you the most basic covering problem. So I'm given a matrix of R rows and C columns. So in this case, I have R equals 4 rows and I have C equals 5 columns. And the matrix has 1s and 0s in it, but for convention and for clarity and for simplicity, I'm just going to draw the 1s because it makes it easier to see. And so row R1 has a 1 for column 2, row 2 has 1s in columns 1, 2, and 3, row 3 has 1 in column 3 and 5, row 4 has 1s in columns 2, 4, and 5. What does it mean to be a cover? A cover says this: choose the smallest set of rows, so that using only those rows, every column has at least a single one in it, which is to say every column is covered by the selected rows. Now, it's okay to have more than one row. It's okay to have more than one in a column. It's just not okay to have no ones in a column. And so if I were to do a nice simple cover for this matrix, I would choose row 2 and row 4, because as we see, row 2 covers column 1, row 2 and also row 4 cover column 2, row 2 covers column 3, row 4 covers columns 4, and row 4 covers columns 5. And so a solution here is row 2 and row 3 as the fewest possible rows that cover all of the columns. There are perfectly nice heuristics to give you very decent, very quick solutions for these. So this is what we're going to turn the expand problem into, because these are not so hard to solve even for things that are pretty big. So what are we going to do? We are going to build something called the blocking matrix. Now, the first thing we're going to do is just look at the structure of the problem. So first, I'm given a function f. All right, so there's my function f. W bar y bar z plus xz plus x bar y z bar plus w bar x y z bar. And that last term, w bar x y z bar, that is the cube that I am going to attempt to expand, because boy, that really stinks as a cube. That's a cube that's covering exactly a single one in the Carnot map. That's probably not a good idea. So the first thing I have to do, which is really quite interesting, is that I have to build a cube cover of the zeros in the function. I have to build a cover of where the function does not make a 1. That has a fancy name. It's called the offset. Why do I need that? Because I need to know what the cube that I am working to expand cannot touch when it expands. And you can sort of get some sense of what the blocking matrix is going to be. I'm going to build a model of, for the cube I am trying to expand, what are the things I could do wrong that would, in this case, overlap a cube in the offset, and then I'm going to, magically do a covering problem that picks the right stuff. So how do you actually build a cover of the offset? And the answer is VLSI CAD Logic to Layout MOOC Programming Assignment number 1. How about that? The URP complement algorithm that we're having you implement, for those of you shooting for the mastery track in this class, the URP complement using a PCN cube notation, this is exactly this step in Espresso. For real. Really, really, really. This is exactly this step in Espresso. This is why we made you do it. So, URP complement is going to give me the gray cubes, and I've got them highlighted here so we can see that they seem bad and ominous. Clearly we don't want to step on these. They seem very unpleasant. So f prime, the complement is x bar z plus wx z bar plus wy bar z. And so we get a cube x bar z, which is in the middle two columns, the left and right, the middle two rows, the left and right columns. We get a wx z bar cube, which is in the third column, the top and bottom rows, and we get a wy bar z bar cube, top row, right two columns. So those are the things we should not be overlapping when we grow this cube. So now we're going to build the blocking matrix, and this is a binary matrix with a very simple structure. It's got one row for each variable in the cube you're trying to expand. So what that means is that it's got a w bar, it's got an x, it's got a y, and it's got a z bar. And roughly speaking, the rows are going to tell us which variables we keep and which variables we get rid of. Because we know that expanding a cube means getting rid of some variables. And it's got a column for each cube in the cover of the offset, which means it's got an x bar z column, it's got a wx z bar column, and it's got a wy bar z bar column. Now, one of the things that I'll just note is, boy, this can be a pretty big matrix. You might not have that many rows, but you could have thousands and thousands and thousands and thousands of columns. It's just the way it works, because you could have a lot of cubes covering that offset. So, one row for every variable in the cube you wish to expand, one column for every cube you don't want to cover in the offset. Put a 1 in the matrix if the cube variable row is different than the polarity of the variable in the cube column. Otherwise, it's a 0, and if it's a don't care, which means just the variable doesn't appear, it's also a 0. And for the zeros, I'm just going to draw a blank because it's just easier to see where the ones are. So let's go look at the first row. Right, so the matrix has rows W bar, X, Y, Z bar, and it has columns X bar, Z, W, X, Z bar, and W, Y bar, Z bar. So W bar has nothing to do with the X, Z cube, and so I'm not going to put anything there. W bar disagrees with the W, X, Z bar cube, so I'm going to put a 1 there because it's got a W in it, and the row is a W bar. Similarly, W bar disagrees with the W, Y bar, Z cube. The X row disagrees only with the first column, X bar, Z. The Y row disagrees only with the third column, WY bar, Z bar. And the Z bar cube disagrees only with the first column, X bar, Z. All right, so that's it. That's the blocking matrix. And the question is, what do I do with this thing to try to figure out how to grow my cube? Well, let's go look. What does a 1 in the blocking matrix row and column really mean? So let's just go focus on the first row. And I've just got that highlighted here with some 1s. What it really means is that if you remove this variable, which is the variable associated with the row, which is W bar, then you might end up overlapping any of the off cubes where you have a 1, depending on what other variables you remove when you expand this cube. And it's sort of a weird reminder sort of a thing that says, please be careful, these are all the cubes you could hit. Why could you hit those cubes? Because you're a W bar. You're on one half of, if you will, this Carnot map. And all these cubes with the W's, they're on the other side. If when you choose to grow this cube, you get rid of the W, you might actually end up on that side of the Carnot map and something bad might happen. So, for example, if you just took this 1 and grew it sideways, to occupy the middle 2 squares of the bottom row of the Carnot map, you would hit the WX-Z bar cube. If similarly you were to expand this cube to occupy the middle 2 squares on the bottom row and the top row of the Carnot map, that's what this the sort of the loop up, loop down diagram in the Carnot map is, you would also hit the WX-Z bar cube, and you would also hit the WY bar Z bar cube. And if you got really lucky and you tried to expand this little tiny 1 in the Carnot map to 8 squares in the Carnot map so that you were the entire middle 2 columns of the Carnot map, you would also hit both of those cubes, WX-Z bar, WY bar Z. So this is what the blocking matrix tells you. It's sort of danger, danger. If you get rid of this variable, be aware, these are the things you might step on. And you cannot hit any of these things. They're the zeros in the function. You're not allowed to cover those. Your cubes cannot circle those things. So given that I can build the blocking matrix and I can find a row cover, right, a set of rows that covers the columns with 1s, what is the rule for how I use that to find a cube expansion? There's a very simple answer. Find the smallest set of rows that covers each column. The product of those row variables is a legal cube expansion. And I will admit it's a little bit backwards. If you keep just those variables in the cover, the rows, you mutually avoid all of the cubes of the offset. And those retained variables, those are the ones that you actually get as your expanded cube. So look at the blocking matrix. What would you pick as a cover? I'd pick the first row and the second row. That's a perfectly good solution. And so the expanded cube would keep W bar and would keep X and would get rid of the other rows that are not in the cover. And WX is one good solution. Turns out there's another solution because I could keep the first row and the fourth row of the matrix. And so I could keep W bar and also keep Z bar. So what do those solutions actually look like as expansions of the cube? Well, the W bar Z bar looks like this. This is W bar Z bar. It is the top and bottom rows of the Carnot map left 2 columns. So that's a completely legitimate expansion of the cube. What does the W bar X expansion look like? Well, that's just the entire column. Just go straight up, capture all four of those ones. So that is the W bar X expansion. Both of those are completely legitimate, completely legal solutions. So it turns out to be a really nice, simple sort of technology. You know, build the blocking matrix, find a cover, a minimum set of rows that puts a 1, at least a 1, single 1 in every single column. The rows that define the cover, those variables, that's what your product is. Now, the one thing I'll note is that you know, the size of this cover may be really big because you know, you could have you know, in a design with you know, 50 or 60 variables in it, you know, you could have tens of thousands of cubes in the offset. Nevertheless, the heuristics for finding these covers are actually quite effective at getting you a, you know, a decent answer really quite quickly. So even though the size of this cover may be really big, you can get a really, really quick answer. So it's a very effective solution. So Espresso is really a collection of just lovely and elegant heuristics, and the reduce, expand, irredundant cycle is the really big deal inside the Espresso algorithms. Reduce ranks the cubes in a clever order, and then you do PCN bit hacking to actually reduce them one at a time. The expand operation ranks the cube in the opposite of that clever order, expands them each individually as a pair of covering problems. One part of the covering problem is just how big can you make the cube, and the other part of the covering problem that I will admit I did not show you says, you know, not only would I like to expand this cube, I'd like to go cover some other cubes so they can go away and become redundant. And that's just another covering problem. Irredundant, amazingly enough, is not only a clever URP algorithm that is a modification of the URP tautology we taught at the beginning of the class, it is also a clever covering problem. So Espresso, very, very pretty set of algorithms and a bunch of other interesting steps that I just don't have time to talk about. There are some other things the method can do. You can minimize several functions at the same time. Each function will be reduced to a two-level form, but some of the product terms will be shared. So you can, for example, have an AND gate that's a product term that's fan out that then is used in, you know, multiple other functions that are all made from a single OR gate. So this means you make the AND product once in hardware, connect it to many OR gate outputs, and you can save some hardware. And you can also handle conventional don't cares. So we showed you about input don't cares that are really just pattern matches to make the truth table specification easy. You can also just specify a row of the truth table as being a don't care. That just means that the output is equal to a don't care. It means the hardware can make a 1 or a 0 for this output because you really don't care. Typically, you do not believe that that input can happen, so let the optimizer choose whether to let the hardware make a 0 or a 1. And so you can actually get better hardware that way. How well does all this stuff work? Fabulously well. It's extremely fast, extremely robust. Where does the Espresso algorithm spend its time? So this is just straight out of the Brayton book. The complement operation that you have to do so that you can tell what expansion can't hit. It takes about 14% of the time, and that can be big if there's lots of cubes in the cover. The expand takes almost 30%, depends on the size of the complement. Irredundant takes 12%. Essentials, which is a step we didn't talk about. Some prime implicants, some things in the cover are essential. They have to be there. There's no other way that you can cover some ones in the input space. Turns out you can just go find them first and take them out of the problem, make the problem smaller. Reduce is quick. It's a cube by cube thing. It's 8%. And then there's a whole bunch of other end of the optimizer optimizations that just try to get a little better answer. How fast is this? Tremendously fast. You know, usually 5 reduce, expand, irredundant iterations. It often converges in just 1 or 2 iterations. You can do thousands of cubes. You can do tens of thousands of literals. You can do hundreds of variables, and you can do this in milliseconds, really, you know, way, way less than a CPU second. So this is a really stupendously effective set of heuristics for doing this problem. So that's our summary for two-level logic synthesis. The big idea is it uses heuristics to find good, but not necessarily perfect. We're not going to get the best solution. Sorry. You know, in those graphs that I showed, we're not going to get the very best solution. We're going to get a good solution, but not a perfect solution. Minimal, not minimum, prime and irredundant. You cannot take any of the cubes and make them bigger. You cannot get rid of any of them. Minimal, prime, and irredundant. That's what we're going to get. There's a very famous idea, an iterative improvement idea, reduce, expand, irredundant, reshape the cover iteratively so that each pass through might get you a better answer. It's all done with PCN cube lists, covering problems and URP ideas, which we've actually explained to you now. So you actually know enough to go read a lot of this stuff. So this is great. There's really good progress here, but not every piece of logic is implemented in two-level form. In fact, most logic is not implemented in two-level form. So we need another set of ideas and another set of methods. And so onward now to multi-level logic, which is where most of the real action is.